This is EE300 Linear Circuit Analysis 2, Module 4, Video 2, Low-Pass Filter Design. In this video, we'll review our previous results. We'll look at low-pass filter design conceptually. We'll look at Butterworth filters and Chebyshev filters, and then we'll summarize what we did and look forward to what's coming next. So to review, previously we saw a second-order low-pass frequency response, and we saw the Saddle and key circuit to implement that frequency response. And we had two ways of doing the Saddle and key circuit. We could do the equal elements method, where the two resistors had the same value and the two capacitors had each had the same value, and then the gain of the non-inverting amplifier was determined by the damping ratio of the second order circuit. And then we had the unity gain method, where you had a voltage follower instead of a non-inverting amplifier. And the damping ratio determined how big one capacitor was in terms of the other, and then the damping ratio of the natural frequency and the capacitance determined how big the resistor was. Here we want to do low-pass filter design, and we're going to take a very direct, this is what matters approach to this and try and avoid any nuance. That means we'll be skipping some things that might lead to greater clarity, but this is very much of a, here, if you do this, this is how it works kind of approach. So here's the first order low pass magnitude response. We want to use it to illustrate the basic properties of a low pass filter specification. So that we decided there was a pass band, and here we can define what we were calling the corner frequency, which is where this first order circuit would be down by 3 dB. So that could be the edge of the pass band. And so we're going to say that when the gain is between the magnitude, the maximum value at the DC, and that value divided by root 2, where it's down by 3 dB relative to DC, we're going to call that the pass band of the filter. Then we're going to pick another value of the magnitude, H min, and then when the response is below that, we're going to call that the stop band of the filter. And that'll be for a set of frequencies that are larger than some omega min. And then the space in between, we're going to call that the transition band. Okay, so let's look how we might use this to specify a low-pass filter we're interested in. This is a first-order filter. It rolls off at 20 dB per decade. We need stuff to get down faster, to be blunt, and that's going to take a higher-order filters to achieve that. So how do we specify those? The same way. We're going to take the half-power frequency as the cutoff frequency for our filter. So we're going to have some DC gain, maximum gain, or it's not always going to be the DC gain, but it will be a maximum gain in the pass band. I'm going to call that H max. And the cutoff frequency will be the edge of the pass band, and we want to ensure that between DC and the cutoff frequency, the gain is always between H max and H max over root 2. And then we're going to have a stop band. So we're going to have some H min and some omega min associated with that. And so H min, we're going to say that as long as omega is bigger than omega min, the gain is going to be less than H min. And what's going to drive the design process and what's going to determine the order of these filters is how narrow that transition band is, what the slope and how fast we have to get down, basically. So as we go from the edge of the pass band to the edge of the stop band, and how much additional attenuation is there. The more attenuation you need, the higher the order you're going to have, and the faster you get there, the higher the order you're going to have. Okay, so the basic form of these filters is going to be a gain K in the numerator, and then a polynomial, and we're going to use a normalized polynomial, so we'll have to scale it by the cutoff frequency to get our desired filter. And the Q of n there will sometimes be Butterworth polynomials, and the Q of n will sometimes be Chebyshev polynomials plus 1. They're not perfectly symmetric there. K is just going to be a scale factor, and then Q sub n is an nth order polynomial with a filter for the filter. And if we just use K equals 1, H max would equal 1, omega c would equal 1. But the shape, the Q of n polynomial, is going to determine the pole locations. And then when we pick omega c different than 1, that's just going to scale those in or out closer to the origin or away from it. And really two different kinds of filters we're going to talk about today. The Butterworth filter, where the poles, the roots of that polynomial, are equally spaced on the circle, and the Chebyshev, where the poles are spaced on an ellipse. So once you determine the necessary gain and what polynomial you're going to have, how big it is, the order of the polynomial is usually the matter of import. Then you design circuits out of first and second order sections, and we've been doing second order sections recently. We've done first order sections before, and you may have to add an additional gain stage after all that to implement the thing. So let's just dive in and do it. Okay, so here's the Butterworth filters. Here's the first three Butterworth polynomials, the first order, second order, and third order. And we're going to write these in products of first and second order terms. So again, we could see how to implement these when the time comes. So you can see that, again, these will be in the denominator of our filter. The numerator is just a constant. So the first order is easy. That's just a pole and these are normalized to have a cutoff frequency of 1. So -1. Second, you got roots at plus and minus 45 degrees from this real axis. Third, now these poles, there's 60 degrees between them and 30 degrees between them and the two closer ones in the j-axis. So the poles of the Butterworth filter are evenly spaced on a semicircle in the negative half plane. Here's the fourth order. Here's the fifth order. Here's the sixth order. So how do we make use of this? Well, the frequency response magnitude has the form 1 over root 1 plus quantity omega over omega c raised to the 2n power. So the picture on the left shows this magnitude h of j omega plotted on a Bode's plot. So we've got frequency on a logarithmic scale on the horizontal axis and 20 log base 10 to the magnitude of h of j omega on the vertical axis. And we can see that all of these go through the corner frequency at minus 3 dB, at the half power point. So just as the specification requires, these filters, regardless of the order, all hit that minus 3 dB point right at that corner. And then for higher frequencies, they roll off at minus 20 dB per decade. So you can see as the order increases from first order filters, second order, third, fourth, fifth, sixth, you get a steeper slope, and that slope is minus 20 dB per decade. You can see the first order hitting over here at minus 20, second at minus 40, third at minus 60. This would hit at minus 80 over here at 1 decade above the corner frequency. So this is, a lot faster than rolling off at 20 dB per decade or 40 like we've been talking about previously. The Butterworth filter is said to be maximally flat. You're never going to find another frequency, another filter that is as flat, as close to a 1 here, without a lot of oscillations or something like that. And so to get our desired filter with a gain H max instead of a gain of 1, you just scale it by H max. So to do the design, we need to know the order of the filter. And so given that form for the frequency response magnitude, we have to have for gain at omega min, since that's that's a monotonically decreasing function of omega. As omega gets bigger, magnitude h of j omega is going to get smaller. So if we meet the constraint at omega min, we're going to meet the constraint in the entire stop band. So the magnitude of h of j omega at omega equals omega min must be less than h min. And so then it's just a matter of solving this for n. And so n is turns out to be the greatest integer, or the ceiling of 1/2 times the ratio of the log of the quantity magnitude h max over h min quantity squared minus 1 over the log of omega min over omega c. This funky square bracket without a lower part there, that's a symbol for the ceiling function. That means the greatest integer in this quantity here. And you'll see how that works in a minute. It's intuitive. You know what it means. You're just not used to seeing a symbol for it. So you plug in your parameters, h max, h min, omega c, and you see what your n is, and then you go back and pick the polynomials for the denominator from that list of ones we had earlier and other published lists of these polynomials. And then you implement second order circuits that will have those polynomials as their characteristic polynomials for that section. You can also see here again, as h max over h min gets bigger, that's going to make this term in the denominator bigger. That's going to make n bigger. As omega min over omega c gets bigger, that's going to make this term bigger, and that will, I mean, it's a little unintuitive here, but that also makes this a bigger N here. It has to depend on the ratio of those two, so here, let's dive in and do an example. So the specifications here, one of the tricks in this art is understanding what the words mean and how to turn those into the symbols you want to work with. So the words will say something like the passband gain is 6 dB relative to the input. That means Hmax is 2 because 6 dB is a scale factor of 2. The cutoff frequency is 1,000 radians per second. Okay, that's one's easy to read. Omega C equals 1,000. The stop band starts at 2,000 radians a second. That's also easy to understand. The attenuation in the stop band is 20 dB relative to the input. So it's a factor of 10 smaller. So Hmin is 0.1. So we plug these into our expression for N. And so that's the log of 20 squared minus 1, the log of 399 over the log of 5,000 over 1,000, which is the log of 5. And now you have the factor of a half there. So we get, that's the ceiling of 4.320, which is 5. 5 is the greatest integer in this expression here. And what I was saying a minute ago, as omega min is bigger than omega c. So as this gets smaller, the term in the denominator gets smaller, I should have been saying. That makes the overall ratio get bigger, and that's why N depends on not just the distance between Hmax and Hmin, but also the distance between omega min and omega c. So we have to build a fifth order circuit. Okay, so we go back and find the fifth order polynomial, b sub 5. We want to normalize it by the cutoff frequency 1,000. So everywhere there was an S plus, we just put S over 1,000. So we get first order section, second order section, second order section. So it's a fifth order, it's a first order, 2 second order sections, and 1 first order section. It has to have an overall gain of 2. Let's do this with Saddle key equal elements. So to get omega 0, which is the cutoff frequency, or the corner for the center frequency for the resonance in each of the second order sections, equal to 1,000, we know we pick R times C equal 1 over omega C. So we can pick R equals 1 kilo ohm, C equals 1 microfarad. And then these two stages each have a different 2 zeta. So 2 zeta is 6.18 in this stage. So mu1 will be 3 minus 0.618, which is a 2.382. And then mu2 for the second order stage would be 3 minus 1.618, which is 1.382. We then have the issue of scale factors. We know that the equal elements is going to give us a gain mu. So this section has a gain mu1, the other section has a gain mu2, and the product of those is actually bigger than 2, bigger than our specification. So we need to get rid of that. We also have to implement the first order dynamics with a pole at minus 1,000 there. And so we need a first order gain of 2 over 3.292, which is 0.608. And then we need the transfer function to be 0.608 over S over 1,000 plus 1. We factor out the 1 over S, and so we get 0.608 over S over 1 over 1,000 plus 1. So then we do our scaling. This is the resistor. This is the capacitor. We can split the 0.608 up into 0.608 and 0.392, and then invert those, and there's scaling to be done and the like. But the overall circuit, here's the 1 k ohms and the 1 microfarads and the equal elements. Here's the gain of 2.38. Here's the second equal element Saddle and key stage with the 1 k ohms and the 1 microfarads. And here's the gain 1.38. And then here's the scaling of those parameters in the first order section. And here's the voltage divider at low frequencies between the two capacitors there that gets us scaling back down to 2 at low frequencies, a gain of 2. That's how you do a Butterworth filter design. You pick your parameter, your specifications tell you the order of the filter, and then you say, I'm doing a Butterworth, so I have to do a fifth order Butterworth. And when you do a fifth order Butterworth, then you implement these various second order sections in the transfer function. Let's look at Chebyshev filters. Chebyshev polynomials actually are, you're adding 1 to the Chebyshev polynomial to get the denominator, the characteristic equation for each of these circuits, or for the overall filter. And so the first order is just back to a pole at -1. But that's actually a pole you can argue, and the analysis shows, I mean, and you all aren't going to do the analysis, don't worry about that. But that's the ellipse that goes with that pole at -1. Let's look at the second order, and now you see the ellipse. The poles are now on this ellipse, and they're closer to the j omega axis. You've got a pair of poles closer to the j omega axis, and so you're not going to get the smooth kind of behavior you get in the passband that you do with the Butterworth. You're going to get some rippliness. You're going to, because you get closer to this pole here, and you're going to get a peak in the frequency response there. Third order, again, you've got 3 poles on the ellipse. Fourth order, fifth order, sixth order, etc. The process is the same. We just let's see what these things look like. First, let's look at the odd Chebyshev frequency responses. So here again, the magnitude of the frequency response is 1 over the square root of 1 plus the C of n, this Butterworth, this Chebyshev polynomial squared omega over omega c. Again, we're skipping a bunch of steps here to show that you actually get this result. I'm saying we're going to use the result, and in fact, you don't even have to know so much what this is, except as it ends up determining our cutoff, our order of our filter here. So again, now we see, instead of just, I mean, here's the first order, it looks the same as the first order, but look at the second order. It comes down faster than 40 dB per decade before it starts rolling off at 40 dB per decade, or this is third order, 60 dB per decade. Here's the fifth order. It comes down fast, and then it starts rolling off at 100 dB per decade. You also can see the ripple in the passband, and so for first order, you just have that one. Third order, you go 1, 2, 3, or 1, 2, 3. Some people will count that as 4. You hit the extreme of 4 times for a third order. Fifth order, you hit it 6 times. 1, 2, 3, 4, 5, 6. That's not, again, a big point. The trick here is that it gets you down faster. It rolls off faster than the equivalent order Butterworth. So in here, since the maximum gain is 1 in the passband, we can scale with k equals h max. When we look at the even order Chebyshevs, we see something different. The second order actually gets bigger than 1 before it starts to roll off at 40 dB per decade. The third order, again, it hits the extreme of 4 times, through n plus 1 times, but it comes down here, and so it's going up bigger, and it's getting 3 dB bigger instead of getting 3 dB smaller. Same with the sixth order. So we get this same steep transition like we did with the odd ones, but the passband gain is a factor of 1 root 2 too big, 3 dB too big. So instead of using a scale factor of h max, we have to use a scale factor of h max over root 2 for the even ordered Chebyshev design. So if you do your analysis and come up with an even order, you don't use h max, you use h max over root 2 as the scale factor in the numerator. And when you put these all together and use 1 over root 2 to scale the even order, you see they all stay within 0, but stay within 3 dB below 0 in the passband, and then they all roll off at in 20 dB per decade, but they have this steep transition where they get to that faster than the Butterworth does. So to do the analysis, again, we have the formula for the magnitude of the Chebyshev frequency response. We have the formula for the scale factor. Again, we have since it's monotonically decreasing, the gain must be at omega min must be less than h min. So now we can plug that in, and we have to know some things about these polynomial C sub n. In fact, they have to, for outside the range of argument 1, they act like hyperbolic cosines, and so we can actually exploit that to solve for the value of n. You don't have to do that. It's done for you here. This is one of those formulas you actually just use. So we can say, again, we take the ratio of h max to h min, square that, subtract 1 from it, take its square root, and then we take the inverse hyperbolic cosine of that and take the ratio of that to the inverse hyperbolic cosine of the ratio of omega min to omega c. And again, you see the same properties there. When h min over h max over h min is big, that makes the numerator bigger. When omega min over omega c is small, that makes the denominator smaller, which makes the overall thing bigger. And so then you go back and design circuits to implement the transfer function for the n and the h max you've got. So here, let's do that same problem we did before. H max is 2, omega c is 1,000, omega min is 2,000, h min is 0.1. We plug that into this formula for n. We get the greatest integer in 2.80, which is 3, so we can achieve the same design with a third-order Butterworth filter that took a third-order Chebyshev filter that took a fifth-order Butterworth filter. So we go back and find the third-order Butterworth polynomials plus 1, and that gives us this these terms here. So now we see they had these scale factors in both the first order and then in the second order terms. So instead of being on a circle of radius 1, the poles of this second order section are on a circle of radius 0.9159, and now we're scaling that by 1,000. So here's our two sections. We have an overall gain of 2. We have this S, the first order section, S with a pole at minus 298. And then we have the resonant part, 2 zeta 0.3254, and then omega 0 of 915.9. So it's going to take one second order section. We're going to use sound and key unity gain for this one, and one first order section, which would be a DC gain of 2, have a DC gain of 2. So our 2 zeta is 0.3254, which gives us a zeta of 0.1627. We pick C1, we get we pick 1 microfarad for C1, and C2 is going to be zeta squared C1, so that gives us 0.163 microfarads for C2. R is determined by 1 over zeta omega naught C1, and that turns out to be 615 k ohms, or 6.15 k ohms. The first order section has a gain of 2. We factor the gain of 2 out, and then we just have the voltage divider between the prototype has a 1 farad capacitor in series with a 1 over 298 ohm resistor. We'll scale those in the final design here. So we end up with a 3.36 k ohm resistor and a 1 microfarad capacitor. Here's the gain of 2 that we need overall, because we have a non-inverting, we have a voltage follower back here in the sound and key circuit. Here's the 6.15 k ohm resistors, here's the 1 microfarad, and here's the 0.616, and these are backwards, aren't they? This is actually be the 1 microfarad up here, and this should be the 0.163 microfarad down here. Can't get through a video without a bug, can I? So the upper one should be the one, that's the C1, that should be 1 microfarad. This is C2, it should be 0.163 microfarads. So to summarize, you specify the low-pass filter with these 4 parameters, H max, omega C, omega min, and omega H min. The Butterworth filter is maximally flat, has poles on a circle of radius omega C. The Chebyshev filter has equal ripple in the passband, poles are on an ellipse, and they're closer to the j omega axis than was for the Butterworth. So if you were looking at the time domain response, like you're studying on the current homework, the Chebyshev will meet the spec with a lower order, but it has ripple in the passband, and it's going to have a slower time domain response because the impulse response and step response associated with those poles are going to be longer than the ones for the Butterworth filter. So you get, the Butterworth gives you smoothness and speed. The Chebyshev gives you ripple and some ringiness or delay, a longer response, but you get you there at a lower order. So there's your engineering trade-off there, and you have to learn over experience when one matters more than the other. So next time we'll look at how do you do high-pass and band-pass filter design. This has been Module 4, Video 2, Low-Pass Filter Design, EE300 Linear Circuit Analysis 2.